Okay, my friend, are you ready for the final tool of our data preprocessing toolkit, feature scaling, which will allow to put all our features on the same scale? So that's the what, and let me quickly remind the why. Why do we need to do this? Well, that's because for some of the machine learning models, that's in order to avoid some features to be dominated by other features in such a way that the dominated features are not even considered by the machine learning model. Now, you also need to be aware that we won't have to apply feature scaling for all the machine learning models, just for some of them. Therefore, we won't include this in our data preprocessing template, which I will show you, by the way, at the end of this tutorial. So we will just add this tool in the toolkit because indeed, for a lot of machine learning models, we won't even have to apply feature scaling even if we have features taking very different values. For example, if you already know a bit about the multiple linear regression model, you know that each variable is actually multiplied by a coefficient, in the linear regression equation. And so, if you have variables that take much higher values than others, when learning the coefficients will just compensate by taking small values for the variables that take high values, right? We will explain this more in part 2 regression, but for now, just know that this is a tool that will be applied from time to time for certain machine learning models, but not all the time, as you will see in this course, all right? And also in the previous tutorial, I actually told you that I was about to answer one of the most important questions or most frequently asked questions by the data science community. And I will keep, of course, my promise. I will answer this when it's time, meaning at around the middle of this tutorial. But no worries, all questions about feature scaling will be answered so that you have absolutely no confusion. All right, so we have the what and the why, and now let's proceed to the how. Meaning, how are we going to apply feature scaling? And to answer this question, I'm going to show you the following slide, which are the main two feature scaling techniques that indeed put all your features in the same scale. And these two techniques are, first, standardization, which consists of subtracting each value of your feature by the mean of all the values of the feature and then dividing by the standard deviation, which is the square root of the variance. And this will put all the values of the feature between around -3 and +3, right? All the different features. When you apply this transformation on all the features of your dataset, all your features will take value between around -3 and +3. So that's standardization. And then you have normalization, which consists of subtracting each value of your feature by the minimum value of the feature and then dividing by the difference between the maximum value of the feature and the minimum value of the feature. And so, since this is positive, and this is always larger than this, that means that all the values of your features will become between 0 and 1. All right, so this will result in having values of features between -3 and +3, more or less, and this will result in having all the values of your features between 0 and 1. Now the question is, also much asked by the data science community, should we go for standardization or normalization? Well, we're going to be here very pragmatic. Normalization is recommended when you have a normal distribution in most of your features. This will be a great feature scaling technique in that case. Standardization actually works well all the time. It will do the job all the time. Therefore, since this is a technique that will work all the time, and this is a technique that is more recommended for some specific situations where you have most of your features following a normal distribution, then my ultimate recommendation for sure is to go for standardization. Because indeed, this will always work, you will always do some relevant feature scaling, and this will always improve the training process. So I'm going to teach you this technique. I'm going to teach you on how to apply it on our matrices of features. And I'm saying matrices of features because now we have two matrices of features, which are xtrain and xtest. And since we understood in the previous tutorial that feature scaling must be applied after the split, you understand that we won't apply feature scaling on the whole matrix of features x, but of course on both xtrain and xtest separately. And actually, the scaler will be fitted to only xtrain. And then we'll transform xtest, we'll apply feature scaling on xtest. Because indeed, since X-test is something that we're not supposed to have during the training, but only after, like when going in production, well, we're not allowed to fit our feature scaling tool on the test set, right? By fitting the feature scaling tool on the test set, that means that we're going to get the mean of the whole set and then the standard deviation in the feature. No, we don't have the right to do this because X-test is supposed to be something new, and therefore we'll just get the mean of the values in X-train, then get the standard deviation of the values in X-train, then apply this formula to transform all the values in X-train, and then apply that same formula but with the same mean and standard deviation of the values in X-train to scale the values of X-test. It's really, really important that you understand this, and this is once again to give some further elements of response to that previous question, should we scale before or after the split? All right, so now that we're all clear on this, let's proceed to the implementation of the how, meaning the implementation of feature scaling. All right, so as usual, in order to be as much efficient as we can, we're going to do this with scikit-learn, right? This data science library that has all the tools, and the tool that we're about to use is a class called standard scaler, and which will exactly perform standardization on both your matrix of features of the training set and the matrix of features of the test set. So let's do this. Let's start by importing this class, which we have to take first from, well, scikit-learn, of course, sklearn, and then from which we're going to get access to the pre-processing module, perfect, which is the module that contains that standard scaler class. All right? So then we're ready to import what we want, which is the standard scaler class. Perfect. So now we have the class, and then the natural next step here is, of course, to create an object of the class. I'm about to reveal soon that answer to one of the most frequent questions in the data science community. So let's create this object. We're going to call it SC for standard scaler. And then, well, this object will be created as an instance of the standard scaler class. So I'm taking it here, pasting that right here, adding some parentheses. And good news, here we don't have any arguments to input, because what we simply want to do is get that mean, get that standard deviation, and then apply this formula to all the values in the feature. And for this, we don't need actually any parameters. This will automatically do the job. All right, so then next step. And now, well, now is the time for me to reveal the answer to that question, which is one of the most frequently asked questions in the data science community. And that question is, do we have to apply feature scaling, standardization, to the dummy variables in the matrix of features? This is one of the most frequently asked questions. You will find it everywhere online as well. And once again, actually, the answer is pretty obvious, but only after you get the explanation. So let me tell you the answer. The answer is no. The answer is no because simply, well, remember the goal of standardization or feature scaling in general. It is to have all the values of the features in the same range. And since I told you that standardization actually transforms your features so that they take values between more or less -3 and +3, well, since here our dummy variables already take values between -3 and +3 because they're equal to either 1 or 0, well, there is nothing extra to be done here with standardization. And actually, standardization will only make it worse because indeed it will still transform these values between -3 and +3, but then you will totally lose the interpretation of these variables. In other words, you will lose the information of which country corresponds to the observation. Now we perfectly know that, remember 1, 0, and 0 corresponds to France because that's how it was encoded, and then 0, 0, and 1 corresponds to Spain. But after we apply feature scaling, if we apply it on the dummy variables, we will get nonsense numerical values and we will be absolutely incapable to say which tuple of 3 values here correspond to which country. So we will totally lose the interpretation, and besides, this won't improve at all the training performance because indeed our dummy variables are anyway already between the same scale range as your other variables. You will see online that applying standardization to your dummy variables might still increase slightly the performance, the final accuracy of your model, but I've experimented many times and I've never seen, a considerable difference that would justify here to apply feature scaling on the dummy variables. So really, don't do this. Only apply feature scaling to your numerical values, right? Here we have clearly some variables taking values in a very different range, right? The age goes between 0 and 100 and the salary goes between 0 and 100,000. So clearly here, if it's better for the machine learning model, we have to apply feature scaling, but let's leave these dummy variables alone so that we can keep the interpretability of the model. All right, so that was the other very important questions. Now I've covered everything. There should not be any confusion left in data preprocessing. I'm really glad that you know this, and therefore I encourage you now to press pause on this video and guess what will be the next step to apply feature scaling to our matrices of feature xtrain and xtest. All right, good. So now I'm going to give you the solution. So first of all, we're going to fit our scaler, our standardization tool, on the training set. So I'm taking the training set first, xtrain, all right? And then, since I've just explained that we won't apply feature scaling on the dummy variables, well then that means that we will fit our standard scaler object only on these two columns here containing the ages and the salaries. And therefore here, I'm going to take only the two columns here for the age and the salary, and then of course all the rows. And remember the trick to take all the rows, we just need to add a colon, which means we are taking the range from the lower bound to the upper bound, meaning everything. And then to take the columns, well, be careful. This is what we have to look at, not this, because indeed we want to take this column and this one. And so now the question is, what are the indexes of these columns? Well, remember that indexes in Python start from 0. So this has index 0, then the second column has index 1, index 2, and this one has index 3. The age column has index 3, and the salary column has index 4. But since I want to make this template as much generic as we can, and since when you one-hot encode your categorical variables, they always automatically go as the first column, well, we're going to do something even better. We're going to specify the indexes we want here by 3, which is the index of the age column, and then a simple colon, right? Because this will take the range from the column of index 3, which is the age, up to all the other columns. There is not the -1 here, so this will take all the remaining columns from the age, meaning the age and the salary. Basically, this will take these two columns, and if you have a larger matrix of features with numerical values in your features, well, this will just take all the columns. All right, so that's a little trick, more elegant, let's say. And so now we are, of course, going to use our object, which we called SC, from which, well, we're going to use that fit method that will indeed, for each feature of xtrain, compute the mean of the feature, meaning the mean of the age and then the mean of the salary, and then compute the standard deviation of the feature, the age and the salary. And that's exactly what the fit method will do. It will only compute the mean and the standard deviation of all the values. And then you have the transform method that will indeed apply this formula by, transforming each of the values here of each feature into this value resulting from this formula. All right, so it's important to understand the difference between fit and transform. Fit will just get the mean and standard deviation of each of your features, and transform will apply this formula to indeed transform your values so that they can all be in the same scale. All right, and now the good news is that one of the methods of the standard scaler class is actually fit transform, which of course will proceed to the two tools at the same time, meaning it will fit your matrix of features to get the mean and the standard deviation, and then right after that, transform all the values of the features to turn them into this formula. All right, so let's call this method right away to make it efficient, fit underscore transform, then some parentheses, and now obviously you know what to input inside this fit transform method. Well, that's of course exactly the same as xtrain here, because indeed we will only apply feature scaling to our numerical columns here containing non-integer values, right? Non-dummy variables values. All right, great. So this will apply feature scaling to our two columns of the training set. And now I hope you know what the next step is going to be and you won't fall into the trap. Now we have to also transform our matrix of features of the test set, meaning xtest, this matrix of features. But since this data is like new data which we get, later on in production, well, for this data, we will only apply the transform method because indeed the features of the test set need to be scaled by the same scaler that was used on the training set. We cannot get a new scaler. If we apply the fit transform method here on xtest, we would get a new scaler. And that would absolutely not make sense because xtest will actually be the input of the predict function that will return the predictions, after the machine learning model is trained. And since this machine learning model will be trained with a particular scaler, the scaler applied on the training set, well, in order to make predictions that will be congruent with the way the model was trained, well, we need to apply the same scaler that was used on the training set onto the test set so that we can get indeed the same transformation and therefore, in the end, some relevant predictions with the predict method applied to xtest. So here, it's clearly the transform method that must only be applied, and therefore, what we're going to do to make it efficient, well, we're going to copy this line of code, and just below we're going to paste it. We're going to replace, of course, xtrain by xtest, and then here as well, xtrain by xtest, and then just call, of course, the transform method from that same scaler that was applied on the training set, because indeed this is part of the training, right? Even if we haven't started the training, well, this operation that we apply here on our training set is, the preparation of the training. All right, so I hope it's clear. It's very important that you understand this. And now, well, I have to say congratulations because we're actually done implementing our final tool. And of course, I'm going to show you the result of feature scaling here. So let me create 2 more code cells inside which we're gonna print first xtrain, and then let me copy this, and then we're gonna print xtest. All right, perfect. So let's first run this to apply feature scaling. Perfect, there we go, no execution error. Then let's print xtrain. And of course, we get, well, still the same values for the dummy variables, which are indeed still between -3 and +3. But then our age and salary variables were transformed so that they take new values between -2 and +2. Sometimes you will see values between -3 and +3. Here it's -2 and +2. But anyway, now all our variables are on the same scale, and this will be perfect to improve or optimize the training of certain machine learning models. And of course, you will see exactly which ones they're going to be the further we progress in this machine learning course. So now you know everything. Let's also execute this cell to print xtest. And once again, well, you still have your dummy variables here for the same 2 customers that were here, but then the age and the salary were scaled so that they take, once again, values between -2 and +2. All right. Okay, so great. I'm really happy that we're now done with this data preprocessing toolkit because that means only one thing. That means that we're ready to start the exciting steps of the journey, which is to build machine learning models that will perform amazing predictions. And we're going to start with the regression models, which will predict some continuous numerical values. And we will learn how to do that on different data sets. But before we move on to this next part, I just want to show you the data preprocessing template, which will be so useful for us to tackle in the flashlight the data preprocessing phase for each of our future machine learning models, because indeed you will see that this template was made so that we will only have each time 1 or 2 things to change, and most of the time 1 thing to change, because indeed in this template I included the 3 always used tools that we will use for our machine learning models, which are importing the libraries, right? We will always need these libraries, then importing the dataset, and here appreciate that we will only have 1 thing to change, which will be the name of the dataset, because indeed this line of code will automatically take all the columns except the last one, meaning all your features, and this line of code will take automatically the dependent variable. So here you will only have the name of the dataset to change, and then of course I included this tool because for most of our machine learning models we will have to split the dataset into these 2 separate sets, 1 training set to train our machine learning model and 1 test set to evaluate its performance. And here once again we will actually have nothing to change. So in the whole template we will only have 1 thing to change, which will be the name of the dataset. And that's why this data preprocessing template will be so useful for us, because we will each time tackle the data preprocessing phase in Flashlight. So make sure to have this template ready each time we're going to build our future machine learning models. And now take a good break. You really deserve it after this data preprocessing phase and these answers to the questions that reduce any confusion. So digest it well, and as soon as you're ready to tackle the first branch of machine learning model, which is regression, well, let's continue our journey together in this next part. And until then, enjoy machine learning.